Hello everyone, my name is Huawei too. Today I'm going to talk about my work, Distractor Effects on Crossing-Based Interaction. Crossing is an important paradigm for mouse input, stylus input, and direct finger touch. Unlike classic point-and-click interactions, the basic element of crossing interactions is to draw a stroke through the boundary of a target to trigger an action, as we can see in the demo. Crossing-based interface is a visual-spatial dependent gesture interface. Targets provide visual stimuli so that users can comprehend spatial information to cross the target. Let's take a look at the example on the right. User draw a gesture to cross some menu items to trigger actions. The gesture itself doesn't carry much information. The expressiveness of crossing interactions doesn't rely on the stroke gesture. It depends on graphical targets that the stroke gesture crosses on the interface. In realistic interaction scenarios, intended targets are often surrounded by distractors. Selecting these targets is a typical task on crossing-based interfaces. The images show crossing-based interactions with distractors for checkboxes, radio buttons, dialog boxes, and menus in a Go crossing framework. For example, when crossing item A in the checkbox, item B could be a distractor. Existing fundamental studies of user performance in crossing tasks generally didn't consider the presence of distractors around targets. Therefore, we conducted the first study to investigate distractor effects on crossing-based interaction. This study focuses on typical crossing-based interfaces with items aligned horizontally or vertically. We adopted 6 representative target distractor spatial layouts in our experiment. We also developed 6 quantitative models for these layouts. First, let's take a look at direction constraint crossing. This is a layout without distractors. 2 vertical targets are each crossed from left to right. We used this layout as a baseline. We consider the distractors placed on the left of the target, on the right of the target, and also on the left and right of the target. Here we can see for amplitude constraint crossing, which is to cross 2 horizontal targets with downward strokes. We consider the layout without distractors placed above the target, below the target, and also above and below the target. We conducted an experiment to investigate the effects of distractors on crossing-based interaction. The independent variables were target distractor spatial layouts, target distance, target and distractor width, and spacing between targets and distractors. The dependent variables were completion time and error rates. We found that the presence of distractors slowed down crossing interactions without significantly affecting target crossing accuracy. When target distractor spacing increased to 7.25 mm, its effect on selection time would become insignificant. When spacing is smaller than 11.27 mm, crossing tasks with distractor interference can be regarded as pointing tasks or a combination of pointing and crossing tasks. Regarding model fitting, compared to Fitts law, our proposed models yielded better fits with the experiment data in all 6 layouts, with R-square always greater than 0.95. Also, our models had smaller AIC than Fitts law. Such results confirm the advantage of our proposed models. In this study, we carried out the first investigation into distractor effects on crossing-based interactions. We developed 6 models for 6 crossing tasks with distractor interference. We also provided a set of general guidelines and practical suggestions. That's the end of my presentation. Thank you.